Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Rajani Dhingra with us today. Hey, Rajani.
Hi, Frank. Hi, everyone.
What's your geolocation?
I am at Southern California, Pasadena, to be precise.
Okay, very good. And what is that lovely object behind you as your background?
This is Titan, Saturn's largest moon. And you're looking at Titan's North Pole here in this particular color scheme. It's a spectroscopic image. And I'm going to talk about my research using this image a bit.
Awesome. That'll be cool. So how is the pandemic in Pasadena, LA area? Is it going up?
Yeah, I just to save myself some mental peace, I don't watch much news. I don't go out a lot. So yeah, we are pretty much hunkered down like everyone else.
Yeah, I am definitely bunkered down.
Yeah.
Definitely. So that's a great shirt you got on too. You look so very spacey there.
Yeah, thank you. It was like I'm going on AAS. I need to get my game up.
Very cool.
Yeah.
So Rajni, what do you like to do for research?
So I study in no man's language. I study surface of planetary objects, and I started with our moon, the moon, and then for my PhD, I did icy moons. I
Okay.
did Titan, which is Saturn's largest moon, using spectroscopy. Presently, I'm doing my postdoc at Jet Propulsion Laboratory here at Pasadena.
Cool. Where did you
And
do your PhD work?
I did it at University of Idaho,
Uh-huh.
Northern Idaho.
Uh-huh.
Moscow is the city.
Yes, Moscow in the US.
Yeah, yeah.
Very
So
cool.
right now I'm studying Europa. That's Jupiter's moon for my postdoc.
Awesome. Very cool. And that will lead us to this very lovely Planetary Science Journal paper. So, Rajni, you have the pleasure of being the first PSJ on this YouTube series. And for those who don't know yet, the Planetary Science Journal is the newest AAS journal. It has a couple of unique features to it. One is that it's all open access, it's gold access, and all of the peer reviews are double blind. So it's got a few things. So let's get right into it. And the spatio-temporal variation of bright ephemeral features on Titan's North Pole. And Rajani, take us away.
Okay, thank you, Frank. So this manuscript was a succeeding manuscript to our discovery of bright ephemeral features on Titan's North Pole. The discovery manuscript was published in Geophysical Research Letter an year back, maybe.
Okay.
So I'll just like to talk about the background a little before I dive into this one.
Please.
So bright ephemeral feature basically is, as the name suggests, it's bright. It's on Titan's North Pole, emerges out of a solid land surface. These are broad specular reflections, where specular reflections are like the direct specular reflections, where the incidence and emission are equal. These are broad specular reflections, which is on like a specular cone. The reflection could be anywhere.
Okay.
And the implication or why they are important is when the Cassini system or Cassini spacecraft went to the Saturnian subsystem, it was Titan's South Pole. Sorry, it was Titan's southern summer, the South Pole.
We're getting quite a bit of little pop from your microphone, so you may want to position your microphone so you're not hitting it.
Yes, I think I'll hold this like this.
There we go. Perfect.
Thank you for pointing that out.
It's the one-handed,
Yeah. Forgetting that this is Zoom.
Very good.
Well, so what Cassini saw on the Titan's South Pole during southern summer is a plethora of clouds and the first extraterrestrial rainfall event on the southern pole of Titan. Cool. So the general circulation modelers predicted something very similar for the North Pole during northern summer. And Cassini was there for 13 years, which is like half a Titan year. Titan's year is almost 30 Earth years.
Okay.
So we went through half a season of Titan. So come Titan's northern summer, we were expecting something very similar that we saw in the southern summer, like a lot of cloud activity, probably rainfall event, and we did not see anything. There was no cloud, forget about precipitation. So what happened is when we saw this particular observation, which was the 1/20th flyby of Titan, we saw this bright ephemeral feature, which we predicted as either a wet sidewalk effect like feature, which is basically after a rainfall event, how a wet sidewalk gets, like a sidewalk gets wetted and, reflects at correct observation geometries, or a near surface fog.
Okay.
So that is the importance of this observation.
Cool.
Then we went and dug more into the data and we found more bright ephemeral features. And this manuscript basically talks about the spatial and temporal variation of these features on the North Pole.
Cool.
Yeah, so with that preface, we can dive more into it.
Okay. Should we go to figure 1?
Yeah, I think I've introduced, let's go to figure 1. So on the left, figure 1 is illustrating what I was just saying, that BEF, or bright ephemeral feature on surface, is basically a thin veneer of liquid that hugs the solid surface and makes the solid surface reflective at particular observation geometries. On the right is an image at University of Idaho parking lot, and it was the morning after a big rainfall event had happened. And we were walking, I just clicked a picture like, whoo, that's going on my manuscript now.
Cool.
So the orange arrow shows the specular reflection from the from the back windshield of a car. It's like direct specular reflection. And the yellow arrow shows the broad specular reflection. This whole, solid land surface is reflecting brightly. You would see it when you are driving your car many times.
Yep.
And if you see the sidewalk here is gray or dark, it's not reflecting brightly. So you see this broad specular reflection at particular observation geometries. That's like, so we are lucky that Cassini could see these
Nice.
features.
Nice.
So that's figure 1 for us. Figure 2 basically is kind of cataloging the flybys where we see the bright ephemeral feature. So this is in orthographic projections of Titan. The north is, we are looking at the North Pole here. In this particular color scheme, so when we do the data analysis from VIMS, which is Visual and Infrared Mapping Spectrometer, I'll take a step back here for the audience, and I kind of feel so motivated to leave my microphone here.
Okay.
But Titan has a thick atmosphere, and it's like Earth's atmosphere. It is rich in nitrogen, no oxygen, but methane. And methane absorbs light, so we can't see through the atmosphere, Titan's surface. We cannot. That's why Voyager could not see the surface of Titan.
Okay.
But at certain spectral wavelengths, methane does not absorb light, so we can see through the atmosphere and at the surface. What happens is we color code these atmospheric windows and make these color composites here. So in this color composite, purple is cloud, which is not on the surface. Yes, something orange shown by the yellow arrow is on the surface.
Okay.
So like T119, Frank, that you were pointing out, we could see that something is on the surface, it's huge, and it's reflecting brightly, and that's a bright ephemeral feature. And we say, yes, WSW, which is yes, bright sidewalk. Yeah. So these were the flybys where we saw the wet sidewalk feature or bright ephemeral feature, and there are some which we are not sure, and we have a question mark there.
I have a question.
Yes.
Just related to your first image there, after rain, those reflection features go away as surface evaporates. So how long do these ephemeral features last on Titan?
Right. So for all of those, we don't have a succeeding flyby, but we were lucky enough to have a succeeding flyby for at least 3 of these. And like T119 was recorded 2 Titan days before T120. And 2 Titan days means 1 Earth month.
Okay.
And in those 2 Titan days or 1 Earth month, the ephemeral feature, like it was gone. It was
Okay.
transient. So the longevity would be like 2 Titan days, at least. No, at max.
Okay. Yeah. Right.
Yeah.
Yep. Thanks.
Yeah. So I think next figure would be talking about, the data we had. Do you mind going to the next figure, Frank?
Great.
Oh, or we could look at the table 1 here.
Yeah, sure.
Yeah. So table 1 basically, again, tabulates all the flybys where we saw the bright ephemeral feature. Phase angle is an important parameter here, and you see that all the phase angles are really high. Phase angle is the angle between Sun and Cassini,
Right.
or WIMS, and it wouldn't be in one plane, it could be.
Okay.
And it's a combination of incidence and emission. And if you see, all these images are very high phase, because that is where we could see the broad specular reflection. We see more curvature of Titan, and that's why these are all these observations.
Okay.
And just to
Resolution. Okay.
yeah, the resolution, I would like to point, the resolution is high. It's like 37 kilometer per pixel, which is good resolution for WIMS. Our average resolution is 100 to 150 kilometers per pixel. So this is good.
Yeah.
Good resolution for us.
Very good. Okay.
Yeah. Section 2 talks about data, and then we dive into, each flyby.
Okay.
This was our discovery observation T120, where we first saw the bright ephemeral feature. I would like to, take your attention to 3B first, because it's very clear. It's the image. Okay, this is a polar stereo image. North Pole is pointing out of the screen at you.
Okay.
And this is ISS, which is Imaging System Software. And no, sorry, not software. I'm subsystem. Something I'm forgetting. So this particular instrument on Cassini took images of Titan at one wavelength, unlike a spectrometer. It's like a camera, and it takes it at 0.97 micron.
Okay.
The dark features are the 3 big C's on Titan. That one that you're pointing is Kraken. The heart-shaped one is, that one that you're pointing is Ligeia. The heart one is Punga, and down below is the largest, which is called Kraken Mare.
Okay.
And Mare is the way we the name for sea. On the left quadrant is these little black splotches is what we call Lake District on Titan. So these are the smaller lakes on Titan.
That's great. Okay.
Yeah. Now I'll bring your attention to 3A. And as I said, in this color scheme, purple are the clouds. The yellowish, peachish arrow marks is indicating the direct specular reflection from a lake called Jolotlan Locus. And it's pretty smudged because of our higher resolution, and also because of the forward scattering atmosphere of Titan. It's not like you don't see it as a point, but you see like a big smudge.
Yeah.
Down below, you see the bright ephemeral features extend in orangish. These are really huge, like 120,000 kilometers square area, the surface area.
Yeah. Yes.
Pretty big.
Mhm.
Okay. So when we were looking at T120, we wanted to know, was this feature before in the previous flyby? And that's why we went to, if you go down a figure, the last here. So we looked at T100, I think the only flyby where this region was observed before was in T106, which was like 2 years before, and we didn't see that the region, the bright ephemeral region,
Hmm.
that was not bright, but there was another feature there, which you see in this green amoeba-like, extent in
Mm.
Figure B. Um,
Yep.
And then in figure A, you can see the direct specular reflection in orange.
Yep.
Yes, you can see the extent of the feature, and you also see this direct specular reflection from Crack and Mare. So one thing I want to bring to your notice is every time we saw a bright ephemeral feature, it was accompanied by a direct specular reflection. So we could calculate how far this broad specular reflection was from direct specular reflection. It was almost always very close to the direct specular reflections, and was always accompanied by a plethora of clouds in the same flyby.
Okay.
Um, so that is what this feature is. This image is, this figure is telling us. I will not talk about C and D because it will confuse us now. I'll talk about C and D later.
Nonlinear is good.
Yes. Okay. Um, Well, okay, this is a good one to talk about C and D. So this is T119, which was one flyby before T120. The amoeba-like red thing is showing the extent of this. And yes, and then if we go to D down below,
Okay.
the reason we came up with D was there were two tendrils of this feature that is, protruding itself into the sea and into Kraken Mare. So
Hmm.
if we are saying that, hey, this feature could be a wet sidewalk effect from the surface, then what is this thing that is protruding itself into the mare? So
Yeah.
we wanted to again, so we came up with this new color scheme again to hash out or to disentangle more of surface and atmosphere. And if you look, depends upon the resolution of the screen, how you're looking, but if you look at D, the core of the feature is green, and those tendril like things that are sticking out is very bluish whitish.
Bluish whitish. Okay.
I
Good.
mean, like it's not visible. Yeah, yeah, yeah. So if
Okay.
you,
I can see a little
right,
blue
the
there.
tendril is almost gone. It's not perceptible anymore.
Yeah.
And that tendril, the colors in this color scheme, the bluish whitish thing is in the atmosphere, green is the surface.
Okay.
So from this color composite, we can kind of say that the major body of this feature is still on the surface, and those tendrils look like they are in near surface or in the atmosphere. That is why we came up with this.
Yes. I'm with you.
Okay, if you zoom out, yeah, and if you look at figure C, you can see that the clouds look whitish on the left quadrant. Do you see how they look very whitish and bluish?
Yes.
It's just to like reinforce that something uh, in the atmosphere is bluish whitish in our color scheme,
Okay.
and greenish is on the surface. Again, just telling people that this is on the surface, um, could be near surface.
Yes.
Okay, let's go to T123.
E one, two, three.
Oh, sorry, T121. Okay, this is a really good flyby. If you look at figure A, it's so cloud heavy.
Yeah.
It's all purple. There's so much cloud out there. And then there's a specular reflection you see there. Yes, you've got the knack of my research now, right? You'll know it
Well,
when.
you're communicating so well. I know exactly where to go. Oh,
I'm glad I'm doing that.
I'm not even an
Okay.
expert in this.
Okay, so this one, the yellow arrow points at a feature that we named as Ligeia finger, because it's like a finger pointing into Ligeia mare.
Oh, okay. There
Just call it Ligeia finger.
you go.
And then we saw that big portion of the feature is over Ligeia mare. So then if you look at D, we again used our triple color scheme to
Mm-hmm.
see, does the Ligeia finger look whitish, or like is it still on surface, or is it in the atmosphere? And I wouldn't say that it's all whitish, but a good portion of it looks less green,
Yeah.
is what I'll say.
Uh-huh.
So And then there's another observation, but the takeaway from this color scheme, or this realization that this whole feature is not on the surface, is that these huge, I'm saying feature so many times, these huge structures could be near surface fogs, is
Yeah,
what we want to say, that they wouldn't be totally on the surface. That's what we um, concluded in our manuscript, that uh, it could be rainfall and the wet sidewalk effect, or it could be near surface fog,
right.
both of which basically, the main thing to remember is both of which basically tell us that the atmosphere is interacting with the surface, the only planetary body apart from Earth where this is happening. Maybe Mars it happens, but
Yeah.
mostly, in this kind of,
Uh-huh.
and that is in alignment with the northern summers being approached, with the models predicting more precipitation, models predicting more clouds. So what they are predicting is what we are observing. That is the takeaway of the
Nice.
study. Yeah. We, I think we also tried to calculate what would be the rainfall volume,
Okay.
for this huge feature. I think if you go down, probably,
Okay. We got 123 if you want 13.
yeah. So two more things that we did here was, one, we used a model to predict. Oh, so this is. I'm sorry, I'm kind of going in a different thing. You're showing T123. T123 was, it's a, if you see panel A, it's a high lower resolution image. The pixel size looks very
Yes.
thick and fat, um, big, I should say. So we couldn't clearly, spot, but we still see a bright ephemeral feature that shows in this yellow extent here. But what I was taking the audience to is, we did two things. One, we figured out the surface roughness of these regions using a model.
Okay.
It's a Gaussian model which tells us how much, how we basically predict what would be the surface roughness. And what we find is, and we can only predict it when there is a direct specular reflection in the observation, because direct specular reflection tells us the distance between the specular point, and how much we need to tilt the surface. So direct specular reflection point would be this, and how much do we need to tilt the surface in any direction to get a broad specular reflection. So we figured out, not to talk more about this, that the roughness is 9 to 15 degrees, which basically says that the length scale would be cobbles to pebbles on Earth. So the region would be like this, not like river rock. That would be the roughness that is reflecting like this. And the second thing we tried to figure out is, like that you're showing in the screen, we use this particular equation to figure out how much would the rainfall volume would be for us to see this
Yeah.
um, thin veneer, or like a little puddle out there. And I think we couldn't nail how much would be the volume, but depending upon the longevity of these features, we predict that the rainfall that fell on this huge bright ephemeral feature region that it's covering, the percolation or permeability of the surface is such that all would go down, that nothing will be left on the surface in 2 Titan days. That's
Okay.
what we predicted
Uh-huh.
with our modeling. One thing to note here is, this is a lot of approximation, because we
Sure.
don't have real values and real numbers. These are taking model numbers from some other manuscript, and extrapolating it a little bit and finding out a number for our calculation.
Mhm.
So yeah, we have to take it with a pinch of salt. um, and then I think we dedicated a section in our manuscript for the fog scenario, because we are convinced, or we basically could not totally say that this is on the surface. We are saying that this could be a near surface. And when we say near surface, I'm saying heights of, 1 meter to 10 meter.
Prolonged fog. Mhm.
Yeah. So we discussed that, with our observation, the most probable fog candidate would be precipitation fog that happens, after precipitation has happened, and
Mhm.
this methane vapor comes into contact with air, and then, it's already saturated and it reaches the dew point and, makes these fogs.
Right. Yep.
I think that is what we discuss here. We also say, just, we're throwing in ideas there. This could happen, this could happen. So we say, and it's conceivable that we have these plate like features in the atmosphere that is reflecting brightly, something like aerosols on earth that
Yeah.
reflects brightly.
Mhm.
So we say that. We also had another idea that we didn't write it in the manuscript, that could it be a mirage, like mirages on earth, when we are driving,
Yeah.
if you're driving long distance,
Uh-huh.
we see mirages reflecting brightly. So is it that? But we couldn't, yeah, calculate anything, so we didn't write it in the manuscript. But that was another idea floating in our heads.
I would imagine for a mirage, I mean, usually when you see mirages on Earth, right, your sight line is relatively parallel to the surface.
Ah, you're right. Yeah, it's very grazing incidents.
Right, right. And so here, I think your angles are a little high for a
Just
mirage, but what do I know?
Yeah, no, I mean, yeah, I know as much as you about mirages on Titan. Yeah,
Very cool. Very cool.
yeah.
Well, that's all.
So
You got,
this last figure basically is like, the overall result
okay.
of all it's showing all the extent of the bright ephemeral features. And then down below is a timeline which shows that, when did we actually see
Oh, I see.
these features. The thing to note here in this figure or to take away is all of these overlay the larger seas,
Yeah.
that particular quadrant.
Yeah.
It's probably telling us that this is humidity driven. The humidity might be driving
Hmm.
these features is one thing. And with the more heating of higher thermal insulation at the North Pole due to northern summers, the methane vapor could be driving these features, is what we discuss in our discussion section here. But
Very
if you have more ideas or our audience has more ideas, feel free to reach out to me. We are still working because I want to kind of totally nail it. What height of atmosphere are these features at if they are not at the surface, when they are not at the surface?
Yeah, you need a height differentiator of some sorts. Uh,
Yeah,
okay, very cool. Very cool.
yeah,
So Rajani,
yeah.
you hinted at it a little bit, but where do we go from here, given what you published? Or is there upcoming new data? You mentioned a little bit about some of the theory work that could take place on about heights and that kind of stuff. So if you look in your crystal ball, where should the community go over the next 5 years or so?
Today, Frank, Friday the 13th
Oh,
of the year 2020
I
at 12 p.m.
didn't even appreciate it was Friday the 13th. Very good. Okay.
Oh my goodness. So today, my tea leaves say that a
Yeah.
manuscript doesn't work. I spoke to composite infrared reflectance spectrometer. I hope the name, it's SIRS, that's what we say. This was on board Cassini too.
Okay.
And SIRS is capable of determining temperatures, surface temperatures on Titan.
Hmm.
I collaborated with Sears, people who work at Sears, and we found out something about the bright ephemeral features and the temperatures, and the manuscript is in works. It's with our co-authors as I'm talking to you, and will be submitted soon, probably in a week or two. So
Ooh,
that is something,
awesome.
a good finding we have had.
Yeah.
And then the second thing is my advisor from my PhD has written a radiative transfer code, which can, help understand how how a photon would basically scatter into Titan's atmosphere and then scatter back from Titan's atmosphere.
Mhm.
So we are planning to implement a radiative transfer code to hash this thing out. How what is the height of these features if they are when they are at a height, using the radiative transfer modeling, which is a heavy duty work, but that is
Sure.
something that all of us on the team want to get done.
And I imagine that, I would imagine that the composition of the atmosphere that those rays are going through is not a uniform composition, right? You may have a dominant molecule at one height that is not dominant at a lower height. And so somehow you've got to know the chemical stratification.
Totally. And yeah, the density of the atmosphere, the molecules present, the scattering, yeah, that plays a role. And yeah, it
Well,
will play a role in determining that. Yes.
there's lots of things to work on here.
Yes, lots of things to work on.
Right.
Science.
Good, good. So it's not a done subject. There's lots to do.
Yes, it's not a done subject. Also, the prospect of dragonfly flying to Titan makes it all, like, oh, need to do more, need to do more,
Yeah.
find more work to do, and probably will be able to clearly know what is happening on Titan's surface. So yes,
Very,
what to be done.
very cool. Rajani, I want to thank you so much for spending some time with us and walking us through your really lovely article.
Thank you, Frank, for giving me the opportunity, and thank you, everyone.
All right, everyone. We'll see you on the next one. Okay.
Mhm.
Bye-bye.